Today, I'm going to talk about the research that my lab group does to understand how rainfall patterns have changed during natural climate changes in the past, and try to connect that to how it helps us understand the prospect of changes in water availability in response to human-induced climate change in the future. I'm going to start in the Bonneville salt flats of western Utah, just west of the Great Salt Lake. It's kind of a funny place to start a talk about rainfall and lakes. It's a place that looks like it's been eternally dry. But in fact, it's one of the best places in the world for understanding just how dramatically water availability can change when the climate changes. This evidence is written on the hill slopes that surround the salt flats as horizontal lines. You can see it most dramatically at the top of this hill slope, where it looks like it's just been planed off. These horizontal lines extend like bathtub rings all around the basin. And connecting them all together, you start to see what looks exactly like a bathtub ring. If you take the time to hike up to these horizontal lines, like my collaborator Jay Quaid has done here, you see that many of them are composed of beach rocks with aquatic snails and clamshells in between. Others of them are made of calcium carbonate rocks called tufa. You can see these doming heads on top of boulders here that are in front of Jay. Tufa is basically like the lake equivalent of coral reefs. It's made of calcium carbonate by microbes that lived in shallow, light-filled lake waters. Putting it all together, the wave-cut terraces, the beach rock, the tufa, and you start to see evidence that there used to be a giant lake in this now dry region, almost 1,000 feet deep, and with a surface area roughly the size of modern-day Lake Michigan. This lake, called Lake Bonneville, once covered almost all of western Utah, dwarfing the size of the modern Great Salt Lake and the other lakes in the region. And when it left behind these shorelines as well as the salts that now cover the Bonneville salt flats. And it wasn't alone. Today, most of the basins from Southern California through Nevada into Utah are dry, places where we might try to set land speed records or hold Burning Man festivals. But our research shows that between about 15 and 17,000 years ago, the American West looked something like this, with Great Lakes filling most of these valleys. Now, as someone who's always been fascinated by Earth's history, seeing these shorelines, immediately makes me want to understand what was going on in the climate system that filled these basins up with water, what made the Western United States so much wetter than it is today, and what caused these lakes to dry up. Some of you, though, may have a little bit more trouble seeing why this is relevant. Maybe it's just a fun fact, it's interesting to know, nice for a visitor's center, but not so connected to our modern climate crisis. Well, I would say that it's important to understand, or that we should care about the past because we care about the present and future. This map shows projections of water stress in the mainland United States in 2050. And as you can see, most of the southwestern United States, including some of the regions that once held these Great Lakes, are in dark red or brown because of extreme risk for water stress. Now, projections like these exist for areas around the world, and the relationship between a warming climate and increasing water stress on land is extremely robust, backed up by observations and theory and models. But what still remains an open question is just exactly how much drier it's going to get and exactly where that's going to happen, which are the sorts of information that water managers really depend upon. And part of the reason that those remain open questions is because climate models have a difficult time projecting how rainfall patterns will change at the regional scale. One way to improve models and our understanding of how rainfall patterns respond to climate change is, of course, to go to observations, to compare our theories and models against observations. But unfortunately, the observational record in most of the world only goes back about 100 years. So this is one of the oldest weather stations in North America. It's just south of here in the Blue Hills. And it only started in the late 1800s. 100 years of data may sound like a long time, but it spans only a very narrow range of climatic conditions. Earth's history, of course, is 4.5 or more billion years, and it spans a huge range of climatic variability, from warm greenhouse climates with palms located near the Arctic Circle to snowball climates where ice sheets extended to the equator. Now, none of these past climates is a direct analog for where we're headed. But what they do preserve is a rich record of natural experiments with the Earth system that we can use to test our understandings of how rainfall patterns respond to climate changes. The challenge, of course, is that we don't have any direct data from these climates. We have to rely upon natural archives that encode information about the climate around them as they form, things like tree rings for the more recent past, or ice cores, or marine sediments, or rocks for successively deeper times. My group focuses on climate changes of the last 500,000 years. So that's just the last 1/10,000th of Earth's history, but it's enough time to span a great deal of climate variability, as you can see here in these plots of Antarctic temperature and atmospheric carbon dioxide over the last 500,000 years from Antarctic ice cores, with the Earth swinging back and forth between ice ages and warmer climates like today over this time. And what we try to do is use these past climate changes to map how rainfall patterns around the world responded to them, using natural archives like stalagmites from caves, lake deposits like those from Lake Bonneville, or deep sea sediments, which archive windblown dust from the world's deserts. This involves a good deal of field work, which is by far the most glamorous part of our job. It occupies a very small amount of our time. Most of our time is actually back in the lab, analyzing these samples, trying to determine how old they are, what climatic information they reflect, and how they compare to other records from around the world. One of the places that we've been working most recently is in southwestern California, at the other end of this region of the Southwest that was so much wetter about 15 to 17,000 years ago. This is in the Searles Valley, just west of Death Valley, and it's at the tail end of the Owens River system. And it's been that way for the last several 100,000 years. The importance of the Owens River system and understanding how sensitive it is to climate change is that now Los Angeles gets most of its water from the Owens River system, which is a small part of why this basin is so dry today. Like the Bonneville Basin, it includes perched shorelines with boulders and tufa, like shown here in the foreground of this picture, several hundred feet above the modern, mostly dry lake floor. One of the challenges, of course, of shoreline data is that it's discontinuous. It just offers little snapshots, little bathtub rings. And so to get a more continuous view of the lake's history, we've drilled down into ancient sediments that are buried beneath the valley floor using this time machine or drilling rig. Now, my colleague, Justin Strapp, loves to strap GoPros to anything that he can. And so here he's giving us a drill's eye view of getting these sediments out of the ground. These fantastic drilling technicians were able to get us about 100 meters of sediment, which records about 200,000 years of the valley's history. And then taking that back to the lab, we've now been studying it to record the valley's history over the last 2 ice age cycles. Some of the sediments that come out of this work look like this. So this is about 30 centimeters of sediment core. And you can see this dramatic transition from black, deep lake muds, indicative of a very large lake, to salts over the span of just a few centimeters. What you can hold in your hand here is the drying of one of the American West's Great Lakes right at the end of the last ice age. And as we build these records back in time, we can start to put them in a global context by comparing them to other records of global climate from around the same time. So what these plots show is climate history from about 20,000 years ago to 10,000 years ago. This is the very end of the last ice age. So you can see at the bottom, carbon dioxide coming out of the ocean and into the atmosphere, carbon dioxide rising about 90 parts per million, and global temperatures rising in this compilation in the blue above it. These records that are globally integrated make it look like a very smooth and fairly easy transition. But the lakes that we work with would tell a very different story. So this is one example of a lake level record in the black at the top from a basin in western Nevada, one of the larger of these lakes in the western United States. It shows the lake first rising and then crashing, drying to levels that are very close to today's levels as the world warmed and then kept on warming. So I think one of the most really simple messages that I think comes from this work is simply that we're dealing with a very sensitive system. The last time the world warmed a few degrees C, there were dramatic fluctuations in water availability at the regional scale, not just in the Western United States, but all over the world, and in particular in monsoon regions like India, West Africa, East Asia. The paleoclimate record would not reassure us that warming the world a few degrees C is not a big deal. Now, I want to be clear that things may play out very differently this time. We're starting from a warmer climate than we did 20,000 years ago, and we're adding CO2 to the atmosphere about 100 times faster than natural processes added CO2 to the atmosphere at the end of the last ice age. But the paleoclimate record clearly shows us just how disruptive climate change can be at the regional scale. My PhD advisor, one of my PhD advisors, Wally Broker, he really introduced me to this lake-level research, and he was fond of saying that he put this much more simply. He said, the climate is an angry beast, and we're poking it with sticks. And he even had this little cartoon drawn up to show what he meant. And he's right, but I think what's also really exciting is the potential for the paleoclimate record to allow us to start to dig in and understand how this climate beast really works. One of the ways that we can do that is to take the state-of-the-art climate models, the same ones that we use to project the future, and put them into the conditions of ancient climates, and then use them to interrogate what might have driven these dramatic changes in water availability that we see in our paleoclimate data. That allows us to get at the processes that were really governing climate. It also allows us to see whether these climate models that we're using to project the future can adequately represent the changes we know happened in the past. Quite commonly, more than you'd like, these models have a tough time matching the magnitude and the abruptness of the changes that we see in the paleoclimate record, which is not a comforting thought. So I think that the second and last point that I want to make is just to emphasize the importance of continuing to deepen our understanding of the climate system. The paleoclimate record is incredibly valuable and exciting for its ability to surprise us with changes that are larger, more abrupt than we might expect. Now, I want to emphasize in saying this that our understanding of climate change at the global scale is extremely robust. Rising greenhouse gases lead to rising sea levels, warmer temperatures, ocean acidification, etc. But where one of the real frontiers in climate science is understanding how these climate changes play out at the regional scale that our societies depend upon accurate information about. Which areas are going to get drier, which areas are going to get increased floods, which areas are going to experience heat waves, and by how much. And this is one of the places where the paleoclimate record can really offer ground truthing data to help us improve our ability and to help us test our understandings that drive our future projections. So I just want to put a call out for the need for the next generation of climate scientists, paleoclimatologists, to help us understand where in the world we might be most likely to expect that in the future, lakes that we've come to expect as sort of known parts of the landscape might in the future look like abandoned shorelines like those that fill the American West. So in closing, I just want to emphasize that work like this is made possible by a diverse array of funding sources and a huge number of mentors, collaborators, and students, not all of whom I've been able to list here. Thanks so much for your attention.